So now that we've walked through the ImageStreamGang program, let's kind of take a step back and evaluate the pros and cons of what we've seen. So from the good perspective, the parallel stream version is, surprise, surprise, faster than the sequential stream version. It's not really a big surprise at all, right? Because it's pretty much, these are fairly embarrassingly parallel computations. As you can see, we get different performance here. This is not quite as much of a speed up as we saw with the search StreamGang program, where we were basically seeing, linear or super linear speed up in the number of cores. This is faster, but it's not linear speed up, and that's because there's other sources of overhead going on here than just running things in parallel, right? So you've got number one, we're running on an emulator, so that takes into account something. But secondly, you're also dealing with I/O, so you're reading data, you're downloading data, you're writing data, and so there's synchronization points inside the operating system and the emulator that we have little or no control over, and so that means we're not able to scale up quite as aggressively as we have in the past. It's not the fault of the parallel streams framework, it's just a reality of writing a program. It's kind of Amdahl's law, where your speed up is limited by how much stuff can really run in parallel. So there's a lot of stuff running in parallel, but there's other things that are sequentialized, probably reading and writing to the disk, for example, through the emulator. And so since this is I/O bound, you're not going to get as much of a speed up. Now, if you were really doing this for real, you would come up with some way to make your I/O system as fast as possible, and people would do all kinds of clever tricks down at that level, the hardware level and so on, but we don't do that here. Images are downloaded and processed in parallel on multiple cores. That's good. There's not much of a change to the program. You can see that if you were to look at the sequential version, it would look exactly the same, except it would say stream and not parallel stream. The solution is fairly straightforward. I think you'll agree this is not a whole lot of code. The code is fairly easy to understand. And the nice thing about this code is it maps very cleanly onto the design intent. So we're taking a list of URLs, we're ignoring ones that are already cached, we're downloading the ones that aren't cached, we're applying filters to them, and we're storing the output, right? That's the description in a nutshell. That's what the code looks like. And you could compare and contrast that to lower level ways of doing this that don't use streams, and I think you'd agree there'd be much more accidental complexity blurring the actual behavior. Notice how all the behaviors here are synchronous, very important. So blocking download, right? That means that when you're doing a blocking download, here we check the cache, get the result, download the image, return the result, and so the calling thread will block in these pieces when you're moving along. The flow of control can therefore be read linearly, and that's really cool, right? So you just look at this thing, and in fact, it really does work that way if you think about how a parallel stream works. Each of the URLs, one at a time, will be processed in a separate task by the fork join pool, and it'll just take that URL and then apply all those transformations to it, and then store the results into the non-concurrent collector and put it into a list. So that's pretty cool. Very linear. You can start at the top, just read to the bottom. Everything makes perfect sense. But of course, not everything is unicorns and rainbows, as I always like to say. Even though the parallel streams version is faster than the sequential streams version, there are other ways of being even faster. Now, as you'll see, those are more complicated, but you can't get the best performance always by doing the simplest thing. And that should really come as no surprise. It'd be like being able to remain healthy by eating nothing but a fast food diet, right? It'd be nice if you could do that. There are probably a few people who can do that. Very few people can afford to do that. So in general, there's a trade-off between performance and productivity when you choose amongst the different Java parallelism frameworks. So as a general rule of thumb, and we'll prove this in more detail soon, completable futures are more efficient and more scalable than parallel streams, but they're also harder to program. And that's really the trade-off. As with most things in life, there's a trade-off between making people productive and making computers productive. Now, the good news is, over the years, as hardware has gotten faster, as software infrastructure has gotten more optimized, we feel that trade-off less and less. So with each new generation of technologies, people can afford to focus more on human time for many things, not everything, but many things, and let the infrastructure and the software and the platform and the virtual machine and the hardware and the operating system and all that good stuff optimize things on your behalf. The compiler obviously has a role to play there as well. Okay, so that's basically the end of that video.